with the review of what you studied last week. That is, we finished already the 6th week, so we see what we studied last Wednesday. And last Wednesday we studied 4 fundamental subspaces. The notion is not so many, but however, we have so many skills to do your exercise. So first, I repeat what we need to know. Suppose that we are given a matrix A of size m by n. Then the A is divided into m rows vector and n columns vector. Then with that, we can define what we call the row space of A. That is a subspace of n space Rn, generated by all the row vectors of A, or by formula. You see it here on the screen. The row space of A denoted by Rs of A. That is a set of all linear combination of row vectors of A. Similar to that, we can define what we call the column space of A. And the column space of A is subspace of M space Rm, spanned by all the column vectors of A, or by formula you see it is here. It's denoted by Cs of A. And then after that, that is the two first fundamental subspace of a matrix A. The next one will be the known space of A. The known space of A, it is nothing but the set of all solution of homogeneous system of linear equation Ax equal 0. And it is a subspace of n space Rn, or by formula, it is denoted by ns of A. You look like that. That is a set of all x into n space Rn, so that A multiplied by x will get the column 0. The last one is a left known space. The left known space of A is a known space of A transpose. So the definition is quite similar to the previous one, to the known space. Just the only difference, that is, we replace A by the A transpose. And because of that, the left known space of A will be a subspace of M space Rn, not Rn, like before. So that's all. That is 4 fundamental subspace. So that is all new notion. But however, with that, we have a lot of exercise. You need to find the basis for row space, the basis for column space. You need to find the dimension of the row space, of something like that. And next few slides will explain to you how you can do it. The first one, I put it here. Explain to you that if A and B are two matrices, row equivalent to each other, then they have the same row space. That is the first one. So with that, now, if you are required to find the basis for row space of a matrix A, and the canonical way to find một cách chính thống nhất for you to find a basis for row space of a matrix A, that is, first you apply elementary row operation to transform A into a matrix B in row echelon form. Then on the non-zero row vectors of B will be a basis for row space of A. That is a way for you to do the first kind of exercise. And here is an example. Suppose that you are given a matrix A like that. You are required to find a basis for row space of A. So you can follow the way I explained to you in the previous slide. We apply the Gaussian elimination to transform A into B like that. And B is already in the row echelon form. It has 3 non-zero rows, the W1, W2, and WC. And because of that, W1, W2, WC will be a basis for row space of A. So that is our our conclusion. Yeah. The next one will show you another kind of exercise of your task. Suppose that you are given a set of vectors, and here in example is v1, v2, v3, and you are required to find a basis for subspace generated by those vectors v1, v2, v3. And how you can do it? It is very simple. You put v1 to be the first row, v2 to be the second row, and v3 to be the third row. And if you have so many vectors, you will put it in the rows of a matrix A. Then the subspace spanned by those vectors is exactly the row space of the matrix A. And to find a basis for row space of the matrix A, we know already in the previous slide. So here we do the same way. We apply the Gaussian elimination to, you can transform A into B. And B in the row echelon form now has two non-zero rows, the W1 and W2. And because of that, W1 and W2 will be a basis for row space of A. And it is exactly the basis for the subspace spanned by V1, V2, V3. That is the way you can do with the second kind of exercise. The next one will be you need to find a basis for the column space of the matrix A. We consider again the example in the previous example. A like that. You are required to find basis for column space of A. The first method, the first way, the simple way, and I call it the lazy way. You don't have to think anything else. You just only take transpose of A. And here, A transpose became that one. Then we know already that the row space of A, the column space of A is a row space of A transpose. So now you need only to find the basis for row space of A transpose. And we apply the Gauss elimination to get B. And because of that, W1, W2, W3 here, it will be a basis for column space of A. But however, you have another way to find the basis for column space of A. I prefer the second method. It is here. A is a matrix like that. I don't need to do the transpose. I denoted the first, the second, the third, and the fourth columns by C1, C2, C3, and C4. So first step, again, we apply the Gaussian elimination to transform A into row echelon form. Now, in the row echelon form, matrix B, we consider the columns containing the leading one. We have a three leading one here. And because of that, we have a three columns containing the leading one. That is the column V1, V2, and V4. And because of that, V1, V2, and V4 will be a basis for column space of B. And once again, because of that, the C1, C2, C4, that is a corresponding column in the matrix A, will be a basis for column space of A. So that is the second way to do with that, and I prefer this method to find the basis for column space. Next one, that one is very important thing because it will concern with the next for the second part of the course. That is something about the eigenvalue, eigenvector, and diagonalization. But however, that example will show you the way to solve the system of the homogeneous system of linear equation having infinitely many solutions. That is, the example tell you how to find the null space of a matrix A. Suppose that you are given a matrix A like that, and you are required to find the null space of A. the null space of A is exactly the solution space of A. Means we consider the homogeneous system of linear equation AX equals 0. How you can solve it? You need to find all solution, and you need to write it in the form of a subspace. Then the first one, you apply the Gauss-Jordan elimination to transform A into that matrix. And that matrix is already in row echelon form. And in that, now we pay attention to the leading one. We have the leading one is here and here. And it means that we have two columns containing the leading one. And the other columns, the second column and the first column, will correspond to the free variable. It means that the second variable x2 and the first variable x4, they are free variable. By free, I mean you can give it any value. So here I give x2 to be s and x4 to be t. So whenever you give it s and t here, you can get the solution x3 equal minus t and x1 equal minus 2s minus 3t. So now our solution will be x equal x1, x2, x3, x4. And we write it here. x1 to be here, x2 to be s, x3 to be minus t, and x4 is t. And there is one thing you need to do here, that is, suppose that you know already the solution to be like that, you need to write it in the form of s v1 plus t v2. So you put it s of something plus t of something, and that's something you can take from here. So I will not explain that for you here, but you need to do it by yourself, or you can ask your teacher in the tutor class how you can write it here. But however, here you can get it as v1 plus t v2, with v1 to be that and v2 to be that one. And because of that, now the null space of A, or the solution space of that, equals s v1 plus t v2 with any s and any t in the real number. So that is a way to find the null space of A. Next, we define the notion of rank and the nullity. The first observation saying that for any m by n matrix, the row space and the column space of A always have the same dimension. It means that dimension of row space of A equal dimension of column space of A. And that number will be called the rank of A. And we denote it by that thing. Similarly, the dimension of the null space of A is when we call it the nullity of A and denote it like that. And those numbers related to each other by the following things. The sum of the rank and nullity equal n. N is the number of column of A. Or it says that if we have A is m by n matrix, and suppose that we know already that the rank of A is A, then the solution space of A equals 0 will have dimension n minus A. I summarize it in the formula like that. Now, once again, I want to call your attention to the notion, the leading variable and free variable. It is related to the notion of leading one. So you need to remember what is the leading one. Given a matrix A, then the rank of A will be the number of leading variable or the number of leading one appear in solving the system of AX equals 0. That is the number of non-zero rows in the row echelon form of A. And then the nullity of A, that is a number of free variables in solving a system of ax equals 0. So we have say if you have n variable or n unknown, it divided into leading variable and free variable. Free variable equal the dimension of solution set solution space, and the leading variable will equals the dimension of row space of the column space. That is what I want to tell in this slide. And here I summarize it in a table like that. You need to remember for doing exercise. And after that, I continue to study how we can solve general system of linear equation. By general, I mean it is not necessary homogeneous. It means that the right hand side of the system of linear equation is not necessary to be on 0. It can be something non-zero. Then how you can solve it? Suppose that you are given a non-homogeneous system of linear equation like that. Ax equal b. B is any columns vector. Then how you can find on the solution of the system? It is divided into two steps. The first step, you need to guess a particular solution. Các bạn phải mò ra một cái nghiệm riêng xp. Then you need to consider the homogeneous system of equation ax equals 0. For that homogeneous system of equation, we know already how to find on solution. Chúng ta đã biết cách giải một cái hệ phương trình thuần nhất ở đoạn trước rồi. Then any other solution of ax equals b must be like that. Must be xp plus xh. So we need only to guess one particular solution xp, and then we know on other solution. So that is something about the non-homogeneous system of linear equation. And now suppose that we are given a system of linear equation ax equals b. We need to know when the system is consistent. That is, it has at least one solution. Then here you have one criterion to verify when ax equals b is consistent. It is consistent if and only if b lies in the column space of A. That has been explained during the lecture class. So in order to verify b is in the column space of A is somehow not so simple, because you need to find the column space of A. What is that? And then you to see if b belongs to that one. But however, we have another criterion. It is much easier for you to see. The criterion saying that if we consider the coefficient matrix A and the augmented matrix A bar means we add the right hand side column B on the right side of A to be that. So if the rank of the augmented matrix equals the rank of the coefficient matrix A, then the system AX equal B is consistent. That is what we know about the non-homogeneous system of linear equation. And the last one, the last point we studied last week, that is I summarize some equivalent claim for square matrices. In this slide, I restrict to consider only square matrix, and suppose that A is a square matrix of size n by n. Then the following claims are equivalent. The first one, A is an invertible matrix. The second one, the system AX equal B has unique solution for any column B. The third one saying that AX equals 0 has only trivial solution. And the number 4 claim saying that the matrix A has a rank n. That is the order of also matrix. And the claim number 5 saying that n rows vector of A are linearly independent. And the claim number 6 is n column vector of A are linearly independent. And last week, one of our students helped me to add one more thing, the number 7. That is A has a non-zero determinant. So that is all what we studied last week. And we continue the lecture number 4 from here. Please wait a little. Have you seen it? Have you seen my?
Yes.
Yes,
Yes, I have seen it.
yeah.
Now we are going to deal with the notion coordinate and how we can change coordinate and chain of basis. As I explained to you several times before, that is a vector space will have many bases. We have many bases, not only one basis. So we need to do sometimes with this basis, sometimes with the other basis. But before that, the role of a basis is the following. Suppose that the vector space V is given with a basis B consisting of V1, V2 up to Vn. Now X is any vector inside V. Then we know already that any vector X inside V can be written uniquely in only one way as a linear combination of V1, V2 up to Vn. That is here. X can be written uniquely like C1, V1 plus C2, V2 plus Cn, Vn. It means that the number C1, C2, Cn is determined uniquely by X. Given X, we have only one tuple of X, C1, C2, Cn. And because of that, the number C1, C2, Cn will be called the coordinate of X relative to the basis B. Cho một vector X trong không gian này, nó chỉ viết được một cách duy nhất ở dạng này thôi. Vì thế các cái số C1, C2, Cn được gọi là tọa độ của X đối với cơ sở B. So usually the coordinate will be written in the column, and then we call it the coordinate matrix or column, coordinate column of X. You can see it here. C1, C2, Cn usually is written in the column like that. That is a coordinate column or coordinate matrix of X. And in order to specify that is a coordinate relative to the basis B, we put the B here as a subscription in XB equal to that one. So that is the way we write the coordinate of a vector. Now here is some examples. Here is some examples. Suppose that in 3 space R3, we consider the standard basis. Standard basis means we have that thing S is here. And if you are given X in R3, so what is the coordinate matrix or coordinate column of X? Very easy, because X to be that means it is -2 times of the first one plus 1 time of second vector and plus c time of the third vector. So the coordinate column will be -2, 1, and 3. And you can see that the coordinate depends on the basis. That is, with that basis, we have the coordinate like that one. Now, the next slide will show you something interesting. On the slide, you have the same point, the same vector m in the red letter. On the right hand side and the left hand, on the left hand side and on the right hand side. Now on the right hand side, we consider the basis B consisting of two vectors u1 and u2. Because u1, u2 are linearly independent and generating set, so B is a basis for the plane here. And in this basis, the vector m or the point n has a coordinate 6, 4. You can look at the line here and see the coordinate of m now is 6 and 4. But now on the right hand side, the same point on the same plane, but now we change. We consider a new basis, say B prime, consisting of V1 and V2. V1 is here, V2 is here. Once again, V1 and V2 are linearly independent and they are a generating set. B prime is a generating set for the plane. So B prime is another basis for the plane. But in this basis, the same point like on the left hand side, but has another coordinate. Now M has a coordinate 3, 2, not 6, 4. So you see the coordinate of the same vector of the same point can be different if we consider it in different bases. That is very important thing. Now, once again, we consider the 3 space R3, but now we consider the non-standard basis B prime. B prime consisting of 3 vector U1, U2, UC. Here is U1, here is U2, and here is UC. And suppose that we have a vector, a point X inside R3. We need to find the coordinate of that, of X, relative to a new basis B prime. How we can do it? You see that it once again leads to solving a system of linear equation. Now, to find the coordinate of X according to relative to the basis B prime means we need to find the number C1, C2, C3 so that X equal C1, U1 plus C2, U2 plus C3, UC. And we write it here. We substitute all the number in the equation. And then you get, because of that, you get a system of linear equation. Or you can write it in the matrix form to be like that one. And you can solve it here. You can solve it by using Gauss-Jordan elimination. And what you get? You get 5 minus 8 minus 2. That is solution. Then the coordinate of X relative to the new basis B prime will be 5 minus 8 minus 2. So that is a way to find the coordinate. It is still very easy. Now you have a problem of change the basis. As I show you in the picture before, that is the same point, the same vector will have different coordinate in different basis. So suppose that you are given a vector V relative to a basis B prime. And then they require you to find the coordinate of the same vector V, but now relative to another basis B. How you can do it? How you can do it? And here is a very simple example. We consider the case we have two bases in a vector space, and vector space V now is R2. So we have in the two space. So B consisting of U1, U2, and B prime is U1 prime, U2 prime. So we have two bases here. First, we consider U1 prime. Because U1 prime is a vector inside V. So it has coordinate relative to B. U1 prime has a coordinate relative to B. I denoted the coordinate by A, B. Similarly, the U2 prime will have a coordinate in B and denoted by C and D. So what does it mean? It means that U1 prime equals A times of U1 plus B times of U2. And the second one means U2 prime equal C times of U1 plus D times of U2. So that is it. Now we know already U1 prime and U2 prime in B. Suppose that we are given V in here. And suppose that we know already the coordinate of V relative to the basis B prime. That is K1 and K2. What do you need to know? What do you need to do? We need to find the coordinate of V relative to the basis B. How we can do it? Okay, we do as follows. V equal that with coordinate like that means V equal K1 of U1 prime plus K2 times of U2 prime. But U1 prime and U2 prime you know already in the previous slide, and we substitute it here. U1 prime equals that, U2 prime equals that, so we get nothing. Now we multiply them together, we do the calculation, you get nothing. Okay, now V equals that number multiplied by U1 and that number multiplied by U2. It means that the coordinate of V relative to the basis B to be that number and that number. That is, the coordinate of V relative to B equal that number and that number. But if you remember the formula for matrices multiplication, that is exactly the product of A, B, C, D multiplied by K1, K2, K1, K2. And the first column A, B here is exactly the coordinate of U1 prime according to the basis B. And the second column is the coordinate of U2 prime relative to this B. And the column here is the coordinate of V relative to B prime. So I am going to generalize on what I show you here as follows. Now we are going to define what we call transition matrix from B prime to B. Suppose that in the vector space V, we are given two bases B and B prime. B has n vector U1 up to Un, and B prime has n vector U1 prime up to Un prime. Then suppose that V has a coordinate relative to B denoted by the column matrix like that, and it has coordinate columns in B prime denoted by that. We call it coordinate column of the coordinate matrix. It's up to you. You can call any name. Now, then those coordinate columns related to each other by the formula like that. V sub B equal P multiplied by V sub B prime. So what is the P? I write it here. The matrix P equals that one. We take the U1 prime. We take the coordinate of U1 prime relative to B. We get the first column here. We take the columns U2 prime relative to B. We get the second column. And so on up to the last one. You take the coordinate column of UN prime in basis B. We get the n columns here. So we get that thing. So that is the formula. Give us the relation between VB and VB prime. And because of that, the matrix P defined like that will become a transition matrix from B prime to B. Ma trận chuyển cơ sở từ B phẩy sang B. Ở đây là cái coordinate của V trong cơ sở B phẩy và sang bên này nó là ma trận cơ sở hay là cái cột, nó là cái ma trận tọa độ hay là cái cột tọa độ của V trong cơ sở B. So that is a transition matrix from B prime to B. And because B and B prime have the same role, hai cái cơ sở B và B phẩy có vai trò như nhau. Therefore, we can exchange B and B prime. Means that we can change from the basis B prime to B, and we can change from the basis B to B prime. We can do by the similar way. That is, we have the following property. Suppose that P is a transition matrix from B prime to B in n space. Then the matrix P is invertible. The matrix P is invertible. The second one, that is, if we consider the transition matrix from B to B prime, it is exactly the inverse of P. The inverse of P. So we see. If we change from B prime to B, you have a transition matrix P. So if you consider the transition matrix from B back to B prime, it will have a transition matrix P inverse. So I summarize it here. B, the basis, consists of vector U1 up to UN. B prime is the basis, consists of U1 prime up to UN prime. And then the coordinate column of V relative to the basis B will be P time of coordinate column of V relative to the basis B prime. Or if we exchange the role of B and B prime, then the coordinate of V relative to B prime will be P inverse multiplied by coordinate of V relative to B. So that is what I summarize of the two slides. And one of your exercise, that is, suppose that you are given two different bases of the same vector space, say of the n space Rn. Then you need to find the transition matrix P from B prime to B. How you can do it? And here the slide show you one way to find it by using Gauss-Jordan elimination. And it is quite similar to the way you use Gauss-Jordan elimination to find the inverse of a matrix. So it is something like that. You write B, and beside of B, you write B prime. Then you apply Gauss-Jordan elimination to transform the first part here into the identity. Then the second part will become something, and that something is exactly the transition matrix B we need to find. So that is a summary of the way how you can use Gauss-Jordan elimination to find transition matrix P. And here is some examples. Suppose that you are given B like that and B prime like that. So it is very, very easy for you because we consider only the two space R2 and we have two bases like that. Then you have three things to do. The first one, you need to find the transition matrix from B prime to B. Second one, suppose that you know already the coordinate of V relative to B prime equal 1, 2, and you need to find the coordinate of V relative to B. And the last one, you need to find transition matrix from B to B prime. Here is a transition matrix from B prime to B, and here is from B to B prime. How you can do it? The first one is exactly what I explained to you two slides before. That is, we write the first part is B, second part is B prime. Then we apply the Gauss-Jordan elimination. You transform the first part into the identity. Then the second part now became that one. And that one is exactly the transition matrix P. That is P equals that, the transition matrix from B prime to B. And you can verify, later you can verify it, the B, because we can apply our formula. Coordinate of V relative to B equal P multiplied by the coordinate column of V relative to B prime. So whenever we find the transition matrix here, we can put it here and multiply with the coordinate of V relative to B prime. You get that one. So that is the reason we need to find. And you can verify that VB prime and VB to be that one by your hand calculation. And the last one, the number C, how you can do it? Just now we can change. Now we put B prime here and B here. And once again applies Gauss-Jordan elimination, we get that one. The first part is already the identity. Then the second part will be transition matrix from B to B prime. And we know already it is the inverse of P. Inverse of P. So it is here. And once again, you can verify with that. So I leave it for you to do by yourself. And the next one is give you some examples. Once again, we look back at the space of all polynomial of degree less than or equal 3. And you need to find the coordinate of that element in standard basis. And then you are required to find the coordinate of the same element. But now relative to a new basis, the new basis is here. And if we apply what we did already, you can find it. It's very easy. So I list here only the reason. I will not write down the calculation here for you. And the next one, that is the case for the space of matrices. The matrix has a standard basis consisting of 4 matrices like that. And now we have a matrix X like that one. And we need to find the coordinate of X relative to the standard basis. And once again, you need to write it here. You write it as a linear combination of 4 vectors in the standard basis. And when you find the coefficient here, the coordinate column of that relative to B will be 5, 6, 7. S. So that is a way you can represent a vector in coordinate whenever you are given already a basis. And also that is the end of the lecture number 4. And after the break, we begin with the lecture number 5. So now we have a 5 minutes break, please. Okay. I am going to show to begin the slideshow. You seen it?
Yes.
Professor.
Yes.
So it forward or just only stand still in the first class, first slide. It
It's
works.
forward.
Okay,
Yes.
thank you. So we begin the lecture number 5. The lecture number 5 deals with the new notion. It has named inner product space. In Vietnamese is không gian với tích trong. Okay, anyway, the Vietnamese terminology and the English terminology are the same for me, and I suppose that is the same for all of you. But anyway, it is sometimes similar to what you study in high school, that is Euclidean space. Similar to không gian, giống như không gian Euclid we study in high school. However, now we begin right now. Now first we only consider the n space Rn, only that. And for any vector in n space, V to be that, a vector in n space is a sequence of number V1, V2 up to Vn. And for that, we define the length of V to be square root of V1 square plus V2 square plus Vn square. I suppose that you know that is somehow familiar to you. If we consider n to be 2 or 3. Anyway, usually sometimes the length can be called the norm. In Vietnamese, a norm means chuẩn, but that is the name norm or length. Now, in case the number n is 2, the length of the V is given by square root of V1 square plus V2 square. I hope that is just a little more familiar to you. Then the length has following property. Okay. The first one is here. The second one, the number 2 is not a property. It just only the name. If a vector has the length 1, we will call it the unit vector. And the number 3 property saying that a vector has the length 0 if and only if V is 0 vector, means all the component is 0. And the property number 4 saying that if we multiply V by a number C, then it has a length. Its length will be absolute value of C multiplied by the length of V. And here is some examples. In the 3 space R3, we consider the vector V given by those number. Then the length of V, we can compute it, and it is exactly the square root of 17 over 17, means it has a length 1, or in other words, V is a unit vector. And in 5 space R5, if you are given a vector V like that, its length will be square root of that one, and it is a 5 by very simple calculation. Now, we know already that in n space Rn, we have standard basis consisting of n vector e1, e2 up to en. That is something you see on the screen. And also, it is very easy for you to verify that all of those vectors has the length 1. So we call it the standard unit vector in n space Rn. And in case of 2 or 3 dimension, it means that on the plane or in the 3 dimension and space, you have standard unit vector usually denoted by I, J, or I, J, and K, like that. Now I want to tell you about the case of two vectors which are apparent to each other. And I suppose I assume that the two vectors are non-zero vectors. And in that case, two non-zero vectors are parallel if and only if they can be written in the following form: U equals C times of V. And because both U and V are non-zero, so C cannot be zero. C can be positive or negative only. If C is positive, we say that U and V has the same direction. And if C is negative, we say U and V have opposite direction. You can imagine it by looking at the geometry. U equals C, V means U and V lying on the same straight line. C is a positive means U and V direct on the same direction here. And C is negative means U will show to this direction and V will show to the other direction. So we have that, something like that. So that is the case for non-zero vectors which are parallel to each other. We have same direction or opposite direction. Next, that is a property number 4 I explained before. So I will not repeat it here. And if you want to see why you can get that, it is explained in the Moodle, in the slide I up on the Moodle. The next one, that is a notion about the unit vector in the direction of V. Suppose that we are given a non-zero vector V in Rn. Then if we take V and we divide it by the length of V, then we get a new, oh, sorry. What's happened? Yeah. If you take V and we divide it by the length, we can divide because V is non-zero, so the length is non-zero. If we divide it, then we get a new vector denoted by U, and that U is unit vector, means U has a length 1. And we call this vector U the unit vector in the direction of V. So that is what we say here. V divided by the length, we get the unit vector in the direction of V. And here is some explanation, just only some calculation. Then the vector V over the length of V will become the unit vector in the direction of V. And the process of finding a unit vector in the direction of V, we call the process that is normalizing the vector V. Now, here is some example. Suppose that we are given a vector V like that. You need to verify if V is unit or not. If it is a unit vector, so you have to do nothing. If V is not yet unit vector, you need to normalizing it, means you need to find a unit vector in the direction of V. So how we can do? V, because V like that, so V has a length square root of 14. So it is obviously it is not unit vector. Then we need to normalizing V by divide V by the length. So finally, you get that vector. Anything is divided by square root of 14. Then you can verify the new vector which has the length 1. So it is a unit vector in the direction of v. Next, the next one, you can define the distance between the two vectors. Suppose that you are given two vectors u and v inside n square I. Then the distance between u and v is defined to be the length of the u minus v. U minus v. And again, we have a property of distance. You can remember that before when we define the length, we have I claim 4 property, but however, essentially we have only 3 property because property number 2 is a name about the unit vector. So we have 3 property for the length. And similarly, we have 3 property for the distance. It is here. You can see the distance is non-negative. It equals 0 if and only if u and v coincide to each other. And duv equals dv u. And here is some example. Suppose that you are given u and v like that. That is a 2 vector in space R3. Then the distance between u and v to be z1. And what I want you to do as homework, that is, please draw the vector u and v in the space. At home, please take a paper and you draw the coordinate OX, OY, OZ, and you see what is u, what is v, and why the distance between u and v to be 3. Then you will have the imagination about the distance between two vectors. Next, we define the dot product in n space. Suppose that you are given two vectors u and v with the coordinate u1, u2, un, and v1, v2, vn. They must be two vectors of the same space, same n space Rn. Then the dot product of u and v is a number denoted by u dot v and is defined by you take u1 multiplied by v1 and then plus u2 multiplied by v2 and so on up to the last one un plus vn. I believe that one is very familiar with Vietnamese students because you know that already in the high school when n equal 2 or 3, that is what you call tích vô hướng in Vietnamese. That you know already in the high school. But here we consider the same thing. We call it by another name is dot product, and you can define it for any number n, not only for n equal 2 or 3. That's all. Suppose that you are given u and v like that. Now, of course, there's a vector inside R4. That one you have not yet studied in the high school, but however, it's nothing new here. Just only apply the formula here. You apply the formula and you could get the reason. U dot v equal minus 7. And here are some property for the dot product. Suppose that we have u, v, and w are vector inside, and c is any number, any scalar. Then we have the following property. We have that commutativity, distributivity, and that one is also something like associativity. However, you have c type of u dot v equal cu dot v equal u dot cv. And that one The number 4, I don't think it is a property that is just by using the formula. And the last line will be the property, I call it the force property. That is a dot product of V and V Echelon is always non-negative. It equals 0 only in the case V is a 0 vector. So we have exactly for the dot product, we have a 4 property for the dot product. Please remember that because we are going to use those 4 products. Now is the notion of Euclidean n space. We are considering the n space Rn. Rn, we know already what it is. Then Rn is a vector space because on that we have a vector addition, we have a scalar multiplication, and now the n space Rn together with that operation and together with vector length and the dot product will be called the Euclidean n space. Không gian Euclid n chiều is Rn together with vector addition, together with scalar multiplication, together with the length and together with dot product. So we have many things like that. And here are some examples for you, very, very simple one. Let U to be that, V to be that, and W to be that, and you are required to compute those numbers. That is in A, B, C, D, E, and it is here. The first one is by definition U dot V to be -7. And for B, C, and D, it just only apply the formula here. You can find it. And the last one, first you need to find U minus 2W, and then you multiply it by U. Whenever you find it, then you can multiply it to U. You get that number. The next slide will show you that is, you don't know what is U and V, but at least you know the product of U and U, V and V, and U and V. Then with that data, you can find the product of U plus 2V multiplied dot CU plus V. That dot product can be computed using that number. And we apply the 4 property for the dot product, and you can find it here. So I will omit it here. I give it for you to practice, and also you will have a lot of exercise of this guy, this type. Yeah. The next I want to explain to you what we call it the Cauchy inequality, Cauchy-Schwarz inequality. The Cauchy inequality is something very famous in the high school. It is formulated like what you have seen on the screen. Suppose that you have A and B is any number, then you have that one. Now, if you consider A to be the product of U1 V2 and B is the product of U2 V1, U, V are number, then we substitute A and B like that in here. What do you get? You get that inequality. Now, once again, we add on both sides with U1 square, V1 square, U2 square, V2 square. Okay. You get that inequality. But then the right hand side will become U1 square plus U2 square multiplied by V1 square plus V2 square. And on the right hand side, here I forget to write one more formula. On the right hand side, it is exactly U1 V1 plus U2 V2. Everything squared. Then because of that, we get, now it becomes inequality, becomes that one, U1 V1 plus U2 V2 less than or equal square root of U1 square, U2 square, and square multiplied by square root of U1. Here is V1 square plus V2 square. Then if you consider U is a vector which coordinate U1, U2, and V is coordinate is a vector which coordinate V1, V2, then that inequality becomes U, V less than the absolute value of dot product U, V less than or equals the U, V, like that. Then we have that we generalize it for any vector in any n space that has named Cauchy-Schwarz inequality. Suppose that U and V are two vectors in n space I. Then we always have the absolute value of dot product between U and V is less than or equal the product of the length of U and the length of V. And here the absolute value. And here is an example. But example now by the concrete number. If you are given U with the coordinate like that and V with coordinate like that, then U multiplied by V equals that. U multiplied by U is 11 and V multiplied by V equals that. Then you can verify the left hand side, the right hand side, and obviously the left hand side is less than the right hand side. That is a Cauchy-Schwarz inequality. Now I am going to define the angle between the two vectors. In high school, you know already that the vector is some geometric object. Then you can define the angle. But now, given two vectors in n space I, means we have two sequence of real number. We can also define the angle. The angle say zeta between two vectors U and V is defined like the cosine of zeta equals dot product U, V divided by length of U and length of V. And here, I suppose that zeta must be a value like between 0 and pi. And look at that. You see that we always require that the length of U and V are non-zero. Means we can define the angle between two non-zero vectors. That is one remark for you. However, even we define like that, I want to look at the geometry. We have five different cases. The first, on the left, we have the opposite direction. Two vectors showing on the opposite direction. On the right, two vectors direct on the same direction. And we have three cases in the middle. Now I explain for you. On the left-hand side, the zeta, the angle equal pi. In that case, we have a cosine equal -1. The next, we have the zeta is between pi over 2 and pi. That is the case when cosine is negative, equivalent to the dot product U, V is negative. And the case in the middle, that is the case when cosine equals 0. That case, we have the angle zeta equal pi over 2. And equivalent to that, we have the dot product U, V equals 0. The next one will be the case when the cosine of zeta is positive. That corresponds to the case when zeta is in between 0 and pi over 2. And the angle zeta then has named acute angle, góc nhọn. And the dot product of U and V is positive. And the last one, you know already, that is the case when the angle zeta equals 0, with the cosine equal 1. And then here I write once again the remark saying that we cannot define the angle between the 0 vector and some other vector. And here is some simple example for you. Given two vectors like that, and you are required to find the angle. And it's here. The square as the length of u and v is given by that, and dot product to be like that one. So in that case, the cosine equal -1 means the zeta equal pi in that case. And if you look at the coordinate here, you will see that those vectors direct to the opposite direction. Now we define the orthogonal vectors. Two vectors u and v in n square Rn will be called orthogonal if its dot product u dot v equals 0. And the vectors, now we consider the vector 0 is orthogonal to any other vector. So it is somehow funny at this point, because we cannot define the angle between the 0 vector and any other vector. But even though the vector 0 is always considered to be orthogonal to any other vector, that is because of the definition here. You see, if you take the dot product between 0 and any other vector, you always get 0, the number 0. So because of that, the vector 0 will be called orthogonal to any other vector. And here is some very elementary examples for you. Suppose that you are working in the plane, the coordinate plane A2. You are given a vector u with the coordinate 4 and 2. And you need to find all vector in A2 which are orthogonal to that one. You can generalize it for any vector in any space. You can consider A3 or An, anything. So you can do as follows. U has coordinate 4 and 2. Suppose that V has coordinate V1 and V2. And U and V orthogonal to each other means that the dot product of U, V equals 0. And dot U dot V equals 0. But U dot V equals that. You multiply them together. 4V1 plus 2V2 equals 0. Then you have to solve the equation. You get that one. That only one equation, even though you can consider it is a system of linear equation, the system consisting of only one equation. You get infinitely many solutions. It is given by that one. Or you can write all the solution will be of this form. If you look at the formula like that, it's somehow not so easy for you to imagine. But the next slide will show you it's very easy to imagine here. The U has coordinate 4, 2, and here 4 and 2. That is U. And what is it? V? V is any vector lying on the purple straight line here. And it is very easy for you to imagine. The notion in the geometry we study already in the high school, and the notion we have just defined here are the same. The next one will be the triangle inequality. Suppose that you are given U and V, two vectors in n square I. Then you have the length of U plus V less than or equals the length of U plus the length of V. Once again, I require you to imagine by looking at the geometry. If you look at the plane, and U and V are two vectors on the plane, you are given two vectors U and V, you can always put them continuously. The vector V continue from the vector U. Then you have something like that. Then U plus V will be the other side of the triangle by two vectors. Then the inequality now becomes exactly the triangle inequality you know already in the high school. In the high school, you have the following one. Given a triangle on the plane, then the length of one side is always less than the sum of the lengths of two other sides. That is the name triangle inequality in the high school. Ở phổ thông, cái đấy các bạn gọi là bất đẳng thức tam giác. Độ dài một cạnh bao giờ cũng nhỏ hơn tổng độ dài của hai cạnh kia. It is exactly that one, that inequality. And it is explained here, you can read it by yourself. And one more thing, that is equality, dấu bằng, appear only if and only if U and V has the same direction, not the opposite direction, have the same direction. You can verify it by yourself. And the next one has named Pythagorean Theorem, định lý Pythagore. It's saying that suppose that U and V are vectors in Rn, then U and V will be orthogonal to each other if and only if you have square of the length of U plus V equal square of the length of U plus square of the length of V. And you are invited once again to illustrate that equality by consider two vectors U and V on the plane, and U and V are orthogonal to each other. Then you will see that one is exactly the Pythagorean theorem you know already from high school. Next, I want to explain to you the relation between the dot product and matrix multiplication. Now, here I write U and V in the columns. That is a vector U in n square n. You can always represent it, or you can always write it as a column matrix, like on the left hand side here, U and V here. Then, if we take the matrix U and take transpose, then the column will become 0. And then you can multiply them together. Now, you can verify that two matrices U and V now can multiply them together. And the reason will be here. The reason will be 1 by 1 matrix, but 1 by 1 matrix is one number because it has only one entry. So you see, on the right hand side is exactly the dot product of U and V, and the left hand side is U transpose multiplied by V. So you can frame it in the red box, and that is a property that give you a relation between the dot product and multiplication of two matrices. Then we are going to define what we call the inner product space. Before that, we study already everything about the dot product in n space, and you have examples. Anything you can get the example from the high school with n equal 2 or n equal 3. You have everything. Now we are going to define what we call the inner product space, không gian với tích trong. So first of all, we need to define the inner product. So what is the inner product? Suppose that we are given a vector space V. Let U, V, and W denote vectors of V. And suppose that C denotes any scalar. Then an inner product on V, that is a function. The function will send a pair of vector UV to a number denoted by UV between a sharp bracket like that. So the function will send U and V, a pair of U and V, to a number U and V between the sharp bracket like that. And the function need to satisfy the following axiom. We require 4 axioms. The first one is commutativity. The second one is distributivity. The third one is some kind of associativity. And the number 4 is we call it the positive determine. It means that the inner product of V and V must be non-negative, and it equals 0 if and only if V is 0 vector. So you see, those 4 properties is exactly similar, is exactly the same like 4 property for the dot product. So because of that, the first examples about the inner product will be the dot product. So that's it. And here I recall you with I call your attention about that. The dot product usually denoted by U dot V. That has named Euclidean inner product. But in general, in any vector space, the general inner product will be denoted by UV between the sharp bracket like that. Now, a vector space V together with an inner product will be called an inner product space. So we need, first we need a vector space, then we need more, that is we need to have an inner product. Then together with inner product, the vector space will become the inner product space. So that is a definition of inner product space. Here is some examples. Example is already known. That is in n space, we take the dot product, but we know already that the dot product satisfy all property in the definition of the inner product. So it is obviously the first examples about the inner product space. And we define that inner product to be the dot product, and that satisfy everything. So it is obviously is an inner product space. I want to give you another example. That one is here. Now we consider A2, not AN, A2 only. Very simple one, n equal to. We define a function like that. For u equal u, its coordinate u1, u2, v to be its coordinate v2, v1, v2. We define the function uv equal u1, v1 plus 2 times of u2, v2. And I am going to show you that one is again an inner product. But you show that, you should remark that that formula is not the usual dot product, because the usual dot product, it must be u1, v1 plus 1 time u2, v2. But here you have 2 times of u2, v2. So we have a new inner product here. Now we verify 4 properties. The first thing is, if you take uv, it equals that one. But then you can exchange the place of u and v, and u and v here. You get v1, u1, 2 times v2, v2. And it is exactly v multiply v u. So the first property is satisfied. The second property is here. Let we take another vector w with the coordinate w1 and w2, then you can verify things here. The third one is here. Again, you can verify it. And the last one is here. It equals 0 if and only if that is 0. So everything everything is satisfied. And because of that, we have the new function we define like that is an inner product, but that is not Eugen's dot product. And finally, I can give you the general claim. Any inner product in n space must be of the following form here. It must be of the following form: C1 of U1 multiplied by V1 plus C2 times of U2 multiplied by V2 up to Cn times of U1 V1. And the most important thing, that is all the number Ci must be positive. And the next slide will show you a counter example. That is in the case one of those things. If you consider a function like that, and you see here we have a coefficient. In Sweden, the coefficient here is a negative, is a -2. Then that one is not an inner product. Why is that? If you consider the vector v with the coordinate 1, 2, 1, then the inner product of v and v, that equal -6. So the property, the axiom number 4 is not satisfied. The axiom number 4 is not satisfied. It means that those formula is not an inner product on asterisk. Now is some property for inner product. We have 3 property like that. I show you here. I will not explain you in the detail, but you can use it in doing your exercise. And we can define, whenever you have inner product, you can define the length of any vector. The length of a vector U is defined to be square root of U, the inner product of U and U. And because of the axiom number 4, the formula under the square root is non-negative, so it makes sense to define like that. And obviously, if you take square of both sides, you will get square of the length of U will be equal to that. Then, similarly to the dot product, now we can define the distance between two vectors U and V. The distance between U and V is defined to be the norm of the U minus V. Or it is a square root of inner product of U minus V and U minus V. Now the angle.
I have a question, please.
Please.
Okay, so an inner product is a function, right?
Yes.
When you take the root of it, so it's a root of the function, the distance between U and V.
Yeah.
Oh, but what happens if the because that function we can have taking the value from it can take a negative value.
Okay, but however, we take you should be careful, because here we take a square root of the inner function, but now you have only U minus V and U minus V. And the axiom number 4, in the definition of inner product requires that the formula under the square root here is always non-negative. You remember that?
Yes.
And then it is makes sense when you take the square root here. You can you should pay attention that I never put square root of U V. Square root of inner product and inside the inner product, two variables are always the same. Always the same. U, or in the next one, it is u minus v and u minus v always are the same. Is it clear?
Yes.
Not quite or something?
Yeah, well, it's something about the inner product still bothers me. So
Really?
yes, because the definition of the inner product is very complicated.
No. It is quite like a dot product. It's quite similar to product. I don't think it is.
So an inner product is just a it's just one vectors multiplied to another vectors.
Mhm.
Okay, so why do we have a difference between the dot production and the inner product?
No, that is because the dot product, that is only one kind of inner product.
Oh,
In a vector space, you can have so many kind of inner product, not only one. So dot product, you can consider it is like a canonical inner product, or you can call it standard inner product.
okay, thank you.
Okay, so let me continue because we are going to finish the class. So the descent is defined like that, and also we can define the angle between the two non-zero vector once again like that. So you see, anything we do with the inner product is absolutely like what we did with the Euclidean n space. We define the angle to be like that, and then we can define the orthogonal by two vectors are considered orthogonal if and only if its inner product equal to 0. But now, once again, you see, on those notion depends on the inner product. If you change inner product, two vectors can be so let me say two vector u and v can be orthogonal in this inner product, but it will not be orthogonal in another inner product. So you see, it depends absolutely on the way you define the inner product. That is the reason why you need to distinguish between dot product and inner product. And here are some other examples, some other notion, that is unit vector, and the way we can if v is not yet the unit, we can normalizing it to get a unit vector in the direction of the vector v. So because we have so many detail in it here, and it is almost finished the time of the class today, so I stop here. And if you don't have any question about the lecture, I can have something to tell you. So first, if you have some question, please ask me, and then I will have something to announce to you. Yes or no? Question, please.
Teacher, I have a question.
Please.
How can we calculate the distance between two vectors that is orthogonal?
You can compute the distance between two vector to any two vector. So you can apply the formula, and then you can see it. For the orthogonal, the most interesting thing that is about the distance. So it will be explained to you in the next week. That is something I don't know how that when relate to the problem, we have the least square problem. That is the application in of linear algebra. But I don't think that I want to explain to you right now. But however, you can have the exercise to compute the distance between the two vectors to any two vectors, and then you can see.
Yes, thank you.
Okay. Somebody asked me in the chat box that is he required to he required to explain again the definition of the inner product, and I suppose that I don't know you in which tutor class. So who is your teacher? Who asked me that? I don't. So you say that your teacher is Miss Vân, so I will ask her to explain to you once again in the class, in the tutor class. But my advice to all of you that is, whenever you have some new notion which is very abstract, you should try to get some examples, some very simple example. Then you will know what it is. What is the meaning of the notion? So that is for you. And some more question, please. Okay, so now I will inform you something. I have something because I know that some of you in the chat box, some of you ask about the midterm exams. I don't. So as a teacher, I don't think that the exam is very important for a course. But however, as a student, any exams, any assignment and exercise is always very important. So the midterm exam, the first thing I can tell you that is we will do it online on the Buddha. That is the first thing. The second thing, that is we cannot do it before say December 8th. December 8th. Why that? Because now on the class of the USDH, now it's time to do the midterm exams, to take the midterm exams. But however, the modern servers of the USDH cannot serve so many students at the same time. So we have to divide it into some time, and we need to choose to register for some time for our midterm exam. So I promise that it cannot be before the December 8th. So that is what I can tell you now.
Professor, do we have our assignment today?
Oh, I suppose that Miss Huyền will send you during the evening. Okay.
Okay.
Now, somebody asked that is something 18 or 19, but I say, I promise that is after December 8 and 18 and 19 or something. I prefer to choose during the weekend on the Thursday or Sunday. It will be somehow we have more place to do it. But however, it depends. It does not depend on us only. It depends on the whole student body of the USDH. Okay. Okay. So I think that it's time to say goodbye and see you next week.
Goodbye,
Thank
Professor.
you and
Professor.
goodbye.
Okay.
Welcome, Professor.
Thank you, Professor.
Yeah,
Bye.
see you. See you.
Professor, thank you.
Yeah.
Goodbye.